We will calculate the most significant integral in complex analysis, using only Green's theorem. When a gamma curve is closed and piecewise continuously differentiable and positively oriented, we recall Green's theorem. If gamma is a piecewise continuously differentiable, closed and positively oriented curve, and f a function, if for the functions a and b the partial derivatives exist and they are continuous for every point of the region enclosed by the closed curve gamma, then Green's formula holds. Where alpha is the region enclosed by the curve gamma. Based on Green's formula we will prove the proposition. If gamma is closed and piecewise continuously differentiable curve in the complex space, if f a complex function, and for the functions u and v the partial derivatives exist and are continuous in the region enclosed by the curve gamma and satisfy the relations, then let's prove it. Without loss of generality we consider the curve gamma to be positively oriented. Then the curve S is also piecewise continuously differentiable and positively oriented closed curve in the R square. Based on the observations we made, let's calculate the integral. Then press pause to see again the Green S formula. Applying the Green's formula to the two integrals we have, where A is the region enclosed by the curve S, then from the relations of the partial derivatives we have, and the proposal was proved. Based on proposition 1 we will prove another proposition. If alpha is a closed piecewise continuously differentiable and positively oriented curve, and B also a closed piecewise continuously differentiable and positively oriented curve, which is located in the region enclosed by the curve A, and the complex function f satisfies the relations of proposition 1, in the region A enclosed by the curves A and B, then let us prove the proposition. Let the line segment NL and the line segment KM. So two closed curves are formed. The curve E, which consists of the line segment N lambda with direction from N to L, from the upper part of the curve B with direction from L to K, from the line segment KM with direction from K to M and from the upper part of the curve A with direction from M to N, and the curve F which consists of the lower part of the curve A with direction from N to M, from the line segment MK with direction from M to K, from the lower part of the curve B with direction from K to L and from the line segment LN with direction from L to N. From proposition 1 for the curve E we have and from proposition 1 for the curve F we have and adding relations 1 and 2 by terms, we have that the terms are deleted because also the terms are deleted because also the sum of the terms gives and the sum of the terms gives. So the sum of relations 1 and 2 by terms gives. And the proposition was proved. Then we will prove that the complex function, which appears in the line integral, satisfies the relations of proposition 1 and 2. That is, for the complex function. Hold the relationships. For every z difference of w, even w, then f takes the form and partial derivatives of the functions u and v are and so. And the proposition was proved. Then we will show that when the curve gamma is a closed positively oriented circle centered at W, then let's prove it. Even the curve then and the proposition was proved. Based on the previous propositions we have proved, we can calculate the line integral, where gamma is a closed piecewise differentiable and positively oriented curve. If W lies outside the region enclosed by the curve gamma, then from propositions 1 and 3 we have that the line integral equals 0. If W lies within the region enclosed by the curve gamma, then we can find a circle centered at W, which lies within the region enclosed by the curve gamma. And taking the positively oriented curve S, on this circle we have from propositions 2 and 3 that